In the last session, we discussed about how to implement the mapping between main memory or RAM with cache memory, so that CPU is able to take the required data item or word from cache itself. There are three different implementations. Of course, you know, it is associative mapping, direct mapping, and set associative mapping. In the current session, let us go through another important topic called virtual memory. The word virtual means it is not physical, it is not available in real time, it is not in real sense, number one, and it is only an illusion to the program. Before we go for the virtual memory, let me tell you about an important concept, how your operating system performs a task. The earlier operating system, what they do, they generally load your program and data into main memory. Assume your main memory is 4 MB, then your program and data to be executed should be less than or equal to 4 MB. If your program size is greater than that 4 MB of primary memory capacity or primary memory size, then your program cannot be loaded into main memory. When a program cannot be loaded into main memory, and of course, then it is not possible for the program to get executed by the CPU. So what's the requirement? If I say the primary memory capacity is M and the program capacity is N or program size is N, M should be greater than or equal to N. If M is 4 MB, program size should be either 1 MB or less than 1 MB or 2 MB or 3 MB or at the maximum 4 MB. M should be greater than or equal to N, where M denotes the size of your primary memory or main memory, and N denotes the size of your program and data. If M is less than N, what does it mean? The size of the program and data is greater than the size of your available memory. That will be the case when M is less than N. In that case, your program cannot be fitted into your primary memory and it cannot be run. So this was the scenario with respect to the earlier operating system. And do remember, the entire 4 MB is allocated to one program. But now we are not having uni-programming environment. We do have multi-programming environment. What is meant by multi? Instead of keeping only one program in primary memory, we keep many programs in primary memory by keeping a portion of your program in primary memory, and the entire program will reside only on the auxiliary storage or secondary memory, like disk, your hard disk or your pen drive for that matter. What happens here? If assuming in the previous case, if the primary memory is only 4 MB, if I have to allocate equally to two different programs, then each program will be able to have only 2 MB space. But the program size is, let me say 8 MB. Available primary memory is 4 MB. My program size is 8 MB. I am going to keep two different programs. Therefore, each program will get equal size of primary, which means that each program will get 2 MB memory space of primary memory, whereas my program size is 8 MB. I know pretty well, my 8 MB program cannot be stored into a portion of your primary memory, namely 2 MB, in the olden cases or in the previous cases or previous scenario. But nowadays operating system, they facilitate the concept of executing a program where the program size is greater than the available primary memory. How much memory space is allotted for the program? For my program, primary memory space allotted is 2 MB, whereas my program is going to be 8 MB. The idea is I have to execute an 8 MB program. When I mean 8 MB program, which includes data, to be processed by the memory space available or allotted to my program is only 2 MB. Let me put this way. My available memory is 2 MB. That's my main memory capacity. My program size is 8 MB. I know full well I cannot load or I cannot store my entire program onto primary memory, because in 2 MB memory space, I cannot store 8 MB capacity. It's not possible. I can store only 1/4. 1/4 means only 25% of my program and data can be stored in primary memory. Therefore, what I do, I am going to divide my program into, let me say, parts. We call each and every part as a page. And what we do, we store only a portion of my program and data they are moved from secondary memory to primary memory, executed for a while. Whenever they are no longer required, then they will be transferred from primary memory back to the secondary memory. So we call these processes sweep in and sweep out. Sweep in means you transfer the required portion of your program. We normally call it as a page. Let me explain a bit later. That will be transferred from secondary memory or auxiliary memory to the primary memory. Then what I do, then the page that was earlier executed by the CPU, if it is no longer required, it will be moved out first, and then the required page will be moved in. So we call it as sweep in and then sweep out. Sweep in means from secondary memory to primary memory. Sweep out means from primary memory to secondary memory. Because why? Because I know I have only 2 MB available. Assume the page size is 1 MB. That means I've got only 2 pages available. My program has got 8 MB, which is equivalent to 8 pages. Assuming each page is equivalent to 1 MB, my program size is 8 MB, equivalent to 8 pages. My primary memory is only 2 MB, equivalent to 2 pages. Therefore, out of 8 pages in my program, I can keep at most only 2 pages. The remaining 6 pages have to be essentially available only on secondary storage. Therefore, what I do, transfer the first 2 pages to primary memory, execute it for some time, and then transfer it back to the secondary memory or auxiliary memory. Transfer the next 2 pages to primary memory, execute it, then transfer it back. Then after some point of time, transfer the next 2 pages to primary memory, execute it, then return it back to the auxiliary storage. And finally transfer the last 2 pages, namely page number, let me say 6 and 7 or 7 and 8 from secondary memory to primary memory, execute it and complete execution. In this fashion, what I do, with my 2 pages available on primary storage, I'm able to execute my program and data whose size is 8 MB equivalent to 8 pages. So this concept, this is called virtual memory. What the user thinks that my entire program of 8 MB has been loaded into primary storage and then executed by CPU. But I know in reality, memory space allotted for my program is only 2 MB and not 8 MB. So what computer does or OS does in turn, it stores only 2 out of 8 pages onto the primary storage at a given point of time, execute them as long as CPU requires it. Whenever CPU demands some other page, which is available on secondary storage and auxiliary storage, then move these pages out of primary storage, bring in the required pages. In this fashion, at every stage, it can have only 2 pages on primary storage. The entire set of 8 pages will be residing only on auxiliary storage, namely disk. My whole program and data consisting of 8 MB will reside permanently on disk. What I do, while executing, the operating system transfers only 2 MB out of that 8 MB, whichever is required by the CPU will be transferred to primary storage. It executes it for a while, as long as CPU is happy with respect to those 2 pages. As long as, when I mean happy, as long as CPU's request is satisfied, it does the job. Once CPU's requirement is not satisfied, those 2 pages will be transferred out from primary storage to secondary storage, and the next 2 pages which are demanded by the CPU will be transferred from secondary storage to the primary storage. This process is called, as I mentioned before, sweep in and sweep out, and there will be considerable amount of time will be spent on sweep in and sweep out time. In generally, we call this a sweep time. So this is going to be during this time when you are moving a page out of primary storage and secondary storage. We are performing an IO operation between secondary and primary. During that point of time, CPU need not wait. It can take up the next program, namely program 2, which is available on primary storage for execution. That is the basic idea behind the concept of multi-programming. When CPU is busy, IO devices remain idle. When IO devices are busy, CPU remains idle. This is a scenario if we keep only one program in memory called a uniprogramming environment. On the other hand, if we keep many programs, if the first program goes for doing IO operation, CPU need not remain idle or waiting for the first program to return. It can take up the next program in the primary memory for execution. If second program also goes for IO operation or doing some other output operation, for example, then CPU need not wait for the first program to return. In case, if it has the third program available on primary storage, it can take a program number 3 for execution. Thereby, you are making the CPU to be always busy instead of keeping it idle or waiting. This will drastically improve the performance of CPU. That's the whole idea behind the concept of multi-programming. The same thing is applicable to virtual memory as well. In general, in the olden operating systems or in olden computer systems, the entire program must be stored in continuous space. It must be the 4 MB allotted must be continuous in nature. Whereas when it comes to virtual memory, the 2 MB space allotted for program need not be continuous. It can be scattered. It can be anywhere. It can be first 1 MB and then the last 1 MB for program 1. And then for program 2, it can be the second 1 MB and third 1 MB. I say, when I mean 1 MB, 1 MB, 1 MB, 1 MB, assume there are going to be 4 1 MBs or 4 MB. It could be 1 and 3 for the first program, 2 and 4 for the second program. That means the memory allotted for the program, they are not continuous memory space, they are scattered. That's the basic idea behind the concept of virtual memory. And most important point, the size of the program and data is greater than the size of the available memory, which gives an impression or which gives an advantage to the end user. You need not bother about your primary memory capacity. You need not worry, oh, whether my program will fit into my system or not. You need not worry about it. Whatever be your program size, the operating system is always there. With the help of OS, it will divide your program into pages. And then depending on the memory space allotted by the primary memory, in the multi-programming setup, it will transfer only the required pages or demanded pages by the CPU from auxiliary storage or secondary storage to the primary storage, execute it in parts or execute it in a staged manner. Thereby, it is able to complete execution of your whole program. But it gives an illusion to the end user as though the entire program has been stored on primary storage and executed by the CPU, but that is not so in reality. That's the reason why we call this concept as virtual memory. Hope things are clear. That is, size of the program N is greater than size of the available memory. N is greater than M. In olden scenarios or in olden systems, olden computer systems, this is not possible. You cannot store if your program size exceeds the available memory capacity, then your program cannot be run by the CPU. But because of the virtual memory concept, this limitation has been overcome, and you are able to execute your program of your size depending on the hard disk capacity. If I say my hard disk capacity is 20 MB, my program and data size can be 20 MB, whereas my available memory is only 4 MB. That means a 20 MB program can be run on a 4 MB primary memory in a phased manner by dividing your program on secondary storage into pages. That will be 20 pages. Each page is of 1 MB. Please understand for example purpose. And there are 4 MB. There is 4 MB available on primary storage, which is equivalent to 4 pages. That means my program and data, it fully occupies my secondary storage, assuming it is 20 MB, and I have only 4 MB space available. That means a 20 MB page has to be fitted onto a 4 MB page. Therefore, what you do at any point of time, you can keep only 4 out of 20 pages onto the primary storage and then executed by the CPU. And this is done by the CPU by operating system or with the help of operating system. And this concept is called the virtual memory concept. Hope things are clear. That's the basic idea behind virtual memory. And more so, the memory space allotted in the case of virtual memory, the memory space allotted for a program need not be continuous in nature. It can be discontinuous or it can be scattered. So these are the two advantages of using virtual memory concept. Let me go ahead with some more terminologies, what we call them as address space and memory space. Address space, whatever the address used by a programmer is called address space. A set of such memory addresses, virtual address, it is called as the address space. An address used by a programmer is called virtual address, and set of such addresses are called address space. Similarly, a physical location, an address in main memory is called a location or physical address. The set of such locations or physical addresses, it is called memory space. Let us come to how implementation is done. Let us see here. Take a look at the diagram 1216 of the book Maurice Manu. Relation between your address space and memory space. You see here, my program size or auxiliary memory capacity is 1024K. It is equal to 2020, 2 power 20. This is my N. And programs main memory capacity is only 32 KB, which is equal to 2 power 15. See, this is 2 power 20. This is 2 power 15. To reference each and every location in secondary storage or auxiliary storage, you require 20-bit address. Whereas to refer each and every location, main memory or primary memory, you require 15-bit address. A 20-bit address has to be mapped with a 15-bit address. That's the basic idea behind the concept of your virtual memory. What we have to do, we have to translate or map a 20-bit auxiliary address or secondary memory address to a 15-bit memory address. So this is the whole concept of virtual memory. Here, we don't have only one program stored. There are two programs stored. Program 1, data for program 1. Data 1.1, data 1.2 pertaining to program 1. For program 2, there is only one data 2.1. Remember, they are in continuous locations as far as auxiliary storage is concerned. When you come to main memory, see, for program 1, the data and program are continuously stored. When you come to main memory, the program is stored in one page and data is stored in another page. They are not in continuous locations. They are in a scattered manner. That is the advantage of using your virtual memory concept. Let us go in for a simple example. This will be easy for you to understand how it gets implemented. Let us consider a program. As I mentioned before, I have a program whose size is 8K. To represent 8K, we require 13-bit address. Therefore, 2 power 13. This is my program size. Each and every page is equivalent to 1 KB. When I mean 1 KB totally, how many KBs are there? My program size is 8 kilobytes. When I mean program, I mean here program and data put together, it is 8 kilobytes. And each page is equivalent to 1 kilobyte. Therefore, how many pages will be there? 8 kilobytes divided by 1 kilobyte, assuming page size is 1 KB. There will be 8 pages. The page numbers are 0, 1, 2, 3, 4, 5, 6, 7. This is what we call them as a logical page. There are 8 pages of my program and data. Whereas when it comes to physical memory or main memory, it is only 4K. When I mean 4K, 2 power 12 is equivalent to 4 kilobytes. How many are there? There are 4 blocks. Block 0, block 1, block 2, block 4. Since there are 4 KB, since it is 4 KB, each block is equivalent to 1 KB. So 1K, block 0 is 1 KB, block 1 is 1 KB, block 2 is 1 KB, and block 3 is 1 KB. Put together, all the 4 put together, it becomes 4 KB. See, my program and data requires 8 pages, whereas the available memory has got only 4 pages or 4 blocks. Therefore, what I have to do, at the most, I can keep only any 4 pages of my program and data onto the physical memory. Need not be continuously stored. For example, page number 0 can be stored in block number 3. Page number 1 can be stored in block number 0. Page number 4 can be stored in block number 1. And page number 6 can be stored in block number 2. That means we don't store them in continuous locations. They can be stored in a scattered manner, depending on whichever block is available at given point of time. Therefore, what we do here, take up this example. It's very simple. This is what we call them as your memory table in a page system using virtual memory. This is my virtual address. How many bits are there? These 10 bits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 2 power 10 is 1024. 1024 is equal to 1 kilobyte. The low order 10 bits represent your offset or line number. The high order 3 bits represent your page number. When there are 3 bits, 2 power 3 is 8. That will be 8 pages. See here, 000 is your first page number. Page number 0. 001 is page number 1. 110 is page number 6. 111 is page number 7. There are 8 pages. Of course, I do know this table is called memory map table. I have to map a 3-bit page number to a 2-bit frame number. How many bits are required with respect to main memory? To represent block number 0, I require the address bits as 00. This is 01. This is 10. This is 11. Why? Because my primary memory capacity is 4 KB. That means there are only 4 blocks available. How many bits are there? 12-bit address. So remember, I have to translate a 13-bit virtual address to a 13-bit memory address to a 12-bit physical memory address or main memory address. So 13-bit address must be mapped onto a 12-bit address. The first low order 10 bits are common. The low order 10 bits, 2 power 13, remove 10 bits from there, 13 minus 10. The 3 bits represent the page number. Here, cut off those 10 bits, 12 minus 10, which is 2 bits. The 2 bits represent the frame number or the block number. See here, you can call it as a frame or a block. The 4 MB memory space is divided into 4 blocks, block 0, block 1, block 2, block 3. To represent block 0, the bits will be 00. To represent block 1, it is 01. To represent block 2, it is 10. To represent block 3, it is 11. Fine. The remaining 10 bits are common. 2 power 13, that is 3 and 10. 2 power 12, it is 2 and 10. I have to map a 3-bit page number to a 2-bit block number. This is done with the help of a table called as the memory mapping table. And of course, in addition, we have got one more bit we call as a presence bit. The presence bit tells you whether this particular page is present in physical memory or not. If it is 1, it is present in physical memory. If the presence bit is 0, it indicates that the corresponding page number 000 equivalent to 0 in decimal is not available on primary storage. So if it is 1, it is available on primary memory. If it is 0, it is not available on primary memory. So this is your memory mapping table. Please remember, this memory mapping table, what it does, it converts a 3-bit page number into a 2-bit block number. So look at this example, 000, presence bit is 0, indicating that page number 0 is not there on secondary storage. It is available only on secondary storage. It's not there on primary storage. 001, that is my page number 1 is available in 11. 11 means it is available in block number 3. And this one indicates that it is available on primary storage. Page number 2, 010, it is available in 00. That means it is available in block number 0. Therefore, remember, my page number 1 is available in block number 3. My page number 2 is available in block number 0. So page number 3, page number 4, they are not available on primary storage. Why? Because the presence bit is 0, indicating that they are not available on primary storage. Page number 5 is available. It is available in block number 1. And the presence bit is 1. Page number 6 is available in block number 2. So remember, page number 2 in block number 0, page number 2 in block number 0, page number 5 in block number 1, page number 6 in block number 2, and page number 1 in block number 3. Only these 4 pages are currently available on primary storage. The remaining 4 pages are not there on primary storage. Your primary memory is now full. Out of 8 pages, we have kept 4 pages on primary storage, which is required by the CPU for execution purpose. Now, what we have to do, we have to map a 3-bit page number to a 2-bit frame number. This is your memory mapping table. This is what we call the memory table buffer register. Memory table, MTBR, memory table buffer register. What it does, when you read, what is the page number here? 101. Is 101 available on primary storage? Check the presence bit. It indicates it is 1, which tells you that page number 101 is available on primary storage. What we have to do next, we have to find out the corresponding block number. What is a block number given here? It is 01. Therefore, 01 is copied onto the memory table buffer register, and the presence bit 1 is also copied. And this is becoming your main memory address. This 01 remains as this 101 is reduced to or mapped onto the frame number or block number as what is 01. And the remaining least significant 10 bits, that is starting with the values 0101, 01, 0011, it remains the same. We normally call this as the offset. See here, this remains the same. So maybe I can draw and show you with a different color. See, so this address and this one remains the same. The 10 bits of your virtual address and the 10 bits of your main memory address, they remain the same. What is the only difference? The most significant 2 digits of your main memory address is obtained from your memory map table. This is called your memory map table or memory page table. What we do here, we take out this page number 101. We find out the corresponding frame number or block number, which is 01. And the 01 is stored on your location. This is what we call them as your main memory address register. So what we do, we translate or we convert a 3-bit page number to a 2-bit block number. The remaining the low order 10 bits remain the same. Go to the memory location, which is block number 1. 01 represents block number 1. Block number 1 has got 1024 locations. Go to the location, get the data, transfer to MBR. MBR means memory buffer register. That's the basic idea behind the concept of your virtual memory. So what we do here, we have got a 13-bit address. We are mapping a 13-bit virtual memory address to a 12-bit primary memory address. How do we do? The least significant 10 bits represent the offset or line number. The most significant 3 bits represent the page number in the case of virtual address. And the most significant 2 bits represent the block number or frame number in the case of main memory. In a nutshell, maybe I can say here, a 13-bit address is mapped onto a 12-bit physical memory address. This is, I can call it as L, logical. I can call this as P, this is physical. A 13-bit virtual address is mapped onto a 12-bit physical address or available address. How do we do? Let me say here, this is a 3 and 10, 3-bit page number and a 10-bit offset. So let me go here, erase this one. Yes. So 3-bit page number and a 10-bit offset. Let me do for your understanding once again. Three-bit page number and 10-bit offset. The 12-bit frame number or 12-bit primary memory address is divided into 2-bit block number and a 10-bit offset. This 10 bits and these 10 bits remain the same. Only difference is this 3-bit. Let me show you the different color. These 3 bits is mapped onto a 2-bit block number or frame number. 3-bit page number is mapped onto a 2-bit block number or frame number. So the 13-bit virtual address is mapped onto a 12-bit physical address which is available. This is what we call them as virtual memory. What do we do here? We make use of memory table. We make use of memory table buffer register. And then we make use of memory table address register. And MBR stands for memory buffer register. So this is the concept of your virtual memory. Hope things are clear. And so let me clean them. What is the understanding? My program size is 8 KB, whereas my available primary memory is only 4 KB. 8 KB is greater than 4 KB, but I execute in parts with the help of operating system and the concept known as what? Virtual memory. So here N is 8 kilobytes, M is equal to 4 kilobytes. N is greater than M. At a time, I can keep only 4 pages onto the primary storage. The remaining 4 pages should be available only on auxiliary storage or secondary storage. That means my whole program, one last point, my whole program of 8 pages, it resides in disk. That's my secondary storage. So this is your main memory. I can call it as your RAM. What is the RAM capacity? It is 4. It is 4 KB. And what is the block size? Each block is equivalent to 1 kilobyte. Each block is equivalent to 1 kilobyte. What do we do? The entire program resides on auxiliary storage. As and when a page is demanded by the CPU, it gets transferred from auxiliary storage to primary storage. And in a phased manner, the whole program and data, whose size is 8 kilobyte, it gets executed on a main memory whose size is 4 kilobytes. That is the concept of execution. And this concept is possible because of virtual memory concept. What is virtual? We don't have 8 KB of primary memory capacity. We have actually only 4 KB. But the user or the programmer has an illusion is the entire program of 8 KB has been stored on to the primary storage and executed by the CPU. But that is not in reality. And this is a concept of virtual memory. Hope you have understood. So let me finally erase all of them. So before I conclude, virtual memory helps the programmer not to be too much bothered about the available primary memory. Your program and data size is independent of the available primary memory. It can be of any size, but still, whatever be the size of your program and data, you need not worry about it. It will be executed in a phased manner or in a, let me say, in a staged manner by the CPU with the help of operating system using the virtual memory concept. That's number one. Number two, the program and data, they need not be continuously stored on the primary storage. They can be stored on any block number or any frame number that is available at that point of time. Memory allotted need not be continuous, it can be scattered. So these are the 2 points you have to keep in mind with respect to virtual memory. Last but not the least, virtual memory is only an illusion, but not in reality. It gives an illusion to the programmer or end user that his program and data, it completely resides on primary storage and executed by the CPU. But that is not happening in reality. Why? Because your program and data size is greater than the size of the available primary memory. In the example what we considered earlier, the program and data size is 8 kilobytes, whereas available memory is only 4 kilobytes. We know pretty well an 8 KB program and data cannot be stored completely onto a 4 kilobyte storage space. That is never possible. But still your program and data gets executed because of this mapping, paging concept, and because of virtual memory being introduced by the operating system. And this is applicable or available in latest computer systems. So this is what I want to suggest you. Hope things are clear with you.